Dear students, in today's video we are going to discuss Gauss law, and the another name for Gauss law is Gauss theorem. Gauss law is very important from examination point of view. In today's video, first of all we will define Gauss law, then we will prove it. After that we will be covering important points to solve the numerical problems. Gauss theorem. Gauss theorem states that total electric flux over a closed surface when it is placed in vacuum is 1 upon epsilon naught times the total charge Q contained inside that surface. Suppose you have a surface in which plus Q charge is contained, then the electric flux phi E will be given as Q inside that surface divided by epsilon naught. We know that phi E electric flux represents the total number of electric field lines crossing the surface. So, if you want to calculate the electric flux for a closed surface, you need the information of the Q inside that surface divided by epsilon naught. From the definition, we need to clear this thing that the Gauss theorem is applicable to the closed surfaces, right? Then the charge Q can be a point charge, it can be a single charge, or it can be a continuous distribution of charges, right? In case of continuous distribution of charges, to find the total charges, we will algebraically add the charges. To prove the Gauss theorem, we have considered a spherical surface. This black circle represents a sphere. We have O as the center of the sphere. At this center, we have placed plus Q charge. P is the any another point which lies on the surface of the sphere, and the distance between the point O and P is R. It is oriented away from plus Q and it has direction R cap. We know that for a positive charge, the electric field lines are outward, and for the negative charge, the electric field lines are inward. This is one of the objective question, that the electric field lines diverge from the positive charge and the electric field lines converge at the negative charge. So electric field lines are outward, so E vector is in the outward direction. Then we apply the Coulomb's law to calculate the electric field, which is Q divided by 4 pi epsilon naught R cap divided by R square. This R cap is the unit vector directed from O to P. So R cap has this direction. Then we need to calculate the electric flux. We need to calculate the phi, and we know that the phi is the combination of electric field vector and dot product with the area vector. So we choose a small area element which is ds, and n cap is the unit vector which is normal to this area element, and the area vector can be written as product of area element and the normal, right? Then we put the value of electric field and area vector in the expression. When we do so, this is the value for electric field and this is the value for area vector. The terms can be taken common. Inside we are left with r cap dot n cap. It is clear from the figure that r cap is outward and similarly n cap is outward. So these two vectors r cap and n cap are parallel to each other, and two parallel vectors, when they are unit vectors, their magnitude is 1, so their dot product will be equal to 1 only. So we use this thing, we put r cap dot n cap is equal to 1 and we have d phi e equal to this expression. Then we integrate on both sides. On integrating, this d phi e is the electric flux for the small area element. When you integrate it, it will give you the complete flux, that is phi e, right? On the another side, in the integration, 1 upon 4 pi epsilon naught is a constant quantity. Q is a fixed charge which you have placed at the center of the sphere. R square is the radius of the sphere which is not going to change. So the terms which are constant can be taken out of the surface integral. Then the integral is left for the ds only. ds is the small area which we have chosen on the sphere. If you are supposed to integrate it for the entire surface, means this entire surface of sphere will be involved, right? And the total surface area of this sphere is 4 pi r square. We substitute the things. 4 pi and 4 pi will cancel out. R square and r square will cancel out. So you are left with your phi e is equal to q upon epsilon naught, where q is the charge which is placed inside the surface of the sphere, right? So it proves the Gauss theorem that the total electric flux is equal to the charge contained inside the surface S divided by epsilon naught. Now, in the previous case, we have taken only one charge, right? But in real problems, you will have multiple charges inside the surface. Suppose we have Q1, Q2, Q3, Qn lying inside the surface. Each will contribute to the electric flux independent of each other. So phi E can be taken as phi E1, the contribution to the electric flux from the charge Q1. Then phi E2 is the contribution to the net electric flux from the charge Q2. Similarly, phi 3 and phi En. So it will be given as Q divided by epsilon naught, and phi E2 will be Q2 divided by epsilon naught. We are implementing Gauss theorem here. So 1 upon epsilon naught can be taken common. Inside you are left with Q1 plus Q2 up to Qn. This thing can be taken in summation, right? This summation of charges inside the surface S will give you the total Q inside the surface S, right? So phi E, the electric flux, is the total charge contained inside the surface divided by epsilon naught. Another way to state is the electric flux is 1 upon epsilon times the total charge Q contained inside the closed surface. On the basis of this information, we conclude that electric flux is dependent upon the charges which are present inside the surface. Suppose this is any arbitrary surface. Q1 and Q2 are two charges which are placed inside the surface. Q3, Q4 and Q5 are three charges which are lying outside the surface S. When you are supposed to calculate the electric flux, there is no contribution to the total electric flux from the charges which lies outside the surface S. So the total electric flux is phi E, Q1, the first charge lying inside the surface, Q2, the second charge lying inside the surface, divided by the epsilon naught. No contribution is taken from Q3, Q4 and Q5. Another important thing is that the location of the charge inside the surface S will not affect the value of surface integral, means that it will not change the electric flux. Suppose this is any spherical surface and Q charge is placed at the center, and in the another case the Q charge is placed near to the boundary of the sphere. Then phi E1 is the electric flux from the first figure and phi E2 is the electric flux from the second figure, and phi E1 will be equal to phi E2, means the location of the charge will not affect the electric flux. The Gauss theorem is mostly implemented to the symmetric charge configurations. In upcoming videos, we will discuss the electric field from a long straight uniformly charged wire and from a uniformly charged sphere and thin infinite plane sheet of charge which is symmetrically charged throughout. There is one problem based upon the Gauss theorem, that how many number of electric lines of forces that radiate outward from 1 coulomb positive charge in vacuum. Means if you have 1 coulomb positive charge, you have placed it in vacuum, then how many number of electric field lines will radiate outward from this plus 1 coulomb charge? That we need to calculate. Okay, so we implement our Gauss law that phi E is equal to Q upon epsilon naught. We put Q is equal to 1 coulomb. Then phi will be electric field lines. The electric flux will be 1 by epsilon naught. We substitute the epsilon naught. We get this as answer. Right. Now a question is for you people that how many number of field lines will be radiated, or if it is positive charge, the electric field lines will be radiated out. If it will be a negative charge, electric field line will converge at the charge. You need to calculate those number of electric field lines for plus 3 coulomb charge and for minus 8 coulomb charge. Please answer in the comment box. We will discuss the answers. Thank you so much for watching.